Well, hello, everyone, and welcome to our technical webinar today entitled Destruction of PFOS under Ambient Conditions. Our presenter is Akshay Parinke. I am your host, Scott Hartzell, and we are glad to have you with us. I'd like to mention just a few housekeeping items before we begin. First, we will be muting all the phone lines during the presentation to try to reduce background noise and give everyone the maximum opportunity to hear what is being presented. If you have a question, there are two options. You can enter the question in the chat feature here in MS Teams, or you can use the raise your hand feature in Teams, and we will get to those questions at the end of the presentation. We will hold all questions toward the end of the presentation, and we'll save some time then. This webinar has been approved for professional development credit. I did post the sign-in sheet in the comments section, or you can contact me directly if you can't find it there, and I'll send it to you offline. And now I'd like to introduce our speaker. Akshay Parinke is a PhD environmental and chemical engineer in Parsons Emerging Contaminants Group. He functions as a subject matter expert focusing on the decomposition of PFAS chemicals, specifically destruction under ambient conditions. His research has been funded by the Water Research Foundation and the Strategic Environmental Research and Development Program. Akshay joined Parsons within the past year, and we are thrilled to have him here and to have him present on this topic today. And with that, I will turn it over to Akshay.
Thank you, Scott, for that introduction. Before we begin the presentation, I would like to take a brief moment to recognize our core values of safety, quality, integrity, diversity, innovation, and sustainability. Talking about sustainability, we had an amazing webinar presentation last month that focused on how we incorporate sustainable solutions into our projects. So if you have missed that, please log into our website and you should be able to access it. For today's core value moment, I would like to talk about diversity and inclusion. I think diversity and inclusion is one of those core values that helps strengthen some of our other core values by ensuring that we provide quality services, innovative and sustainable products. That being said, having been joined the workforce during the time of a pandemic, it certainly presented its challenges. But it's this core value of diversity and inclusion that really helped me get integrated so quickly and work on some amazing projects and brainstorming sessions, some of the new and innovative ideas that we came up with, and we will be showcasing it today in this presentation. So the outline for this presentation is basically an introduction of what PFAS are, what they're made up of, and what are some of its challenges. We will then move on to looking into the degradation of 6,2-fluorotellumosulfonate by conventional oxidation techniques, which is kind of like the easier ones to degrade. We will then move on to a little more challenging PFAS, which is carboxylic-based PFAS, and we'll be using advanced oxidation technologies for that. We would then look into some of our current research and development initiatives that we are undertaking here at Parsons, and we would conclude it with a question and answer session. So for an introduction and on a very wide perspective, PFAS are a class of fluorinated compounds that contain multiple carbon-fluorine bonds with heterogeneous atoms such as nitrogen or oxygen in certain molecules and a functional group at the end, which could either be a carboxylic molecule or a sulfonic group. PFAS are commonly used in firefighting foams primarily because they have the potential to reduce the surface tension of water, and they are a good source for fighting petroleum-based fires. They are also used in Gore-Tex materials because they are water resistant, and they are used in Teflon coatings because they are water and oil resistant. So that makes them extremely useful in many of the products, because of which they are widely found in the environment. And once they get into the environment, they undergo minimum biological transformation. So they end up in many of the treatment plants, and the treatment plants actively have to take an effort to deal with that particular compound. and it's not so easy to do that. We nearly have 6,000 PFAS identified so far, some of which were manufactured and some of which degraded into products that were then identified later in the environment. Let's look into the chemistry of PFAS. So these carbon fluorine bonds that are present in these molecules are extremely strong. They are some of the strongest bonds in organic chemistry with a bond dissociation energy of 130 kilocals per mole. They prefer to stay in the air-water interface. That could certainly be leveraged to develop some removal techniques, but without having that kind of information, applying conventional treatment technologies to PFAS presents its challenges. That being said, when it comes to removal of PFAS, the amount of energy that's required is enormous. And once we develop a technology for a certain class of PFAS, transferring that into another class of PFAS is not really the same. So once something that's developed for carboxylic acids trying to degrade sulfonic acids is a little more challenging within the same time period and the same rates. Often, these compounds require external energy sources. So many of the research that has been conducted often use something like UV or sonolysis or plasma reactors. So that's some of the most promising ones that have been shown to date. Before I talk about the studies that I will be presenting in this presentation, I would like to mention that some of them have been published in the Journal of Environmental Engineering and in the Journal of Environmental Engineering Science. Thanks to the funding provided by the Water Research Foundation and the SERDIP program, we were able to achieve this. All of the analysis were conducted at the Shimadzu Center for Research Technologies, which is at the University of Texas at Arlington. So first, let's look at the decomposition of 6,2-FTS by conventional oxidation. So 6,2-FTS or 6,2-fluorotellumosulfonate is commonly found in AFFF sites, and they are often a degradation product of a longer chain molecule, which is an amide. They present two carbon hydrogen bonds, and those are the bonds that I have highlighted on the image on the right. So the two nodes that you see are the carbon atoms which have hydrogen atoms connected to them. So those carbon hydrogen bonds present a weak link in this molecule, and they are susceptible to microbial degradation. And once they degrade in the environment, they are often found as perfluorinated compounds. So essentially, removing the carbon hydrogen bonds, the molecule solely consists of carbon fluorine bonds and a functional group at the end. So when we started doing these reactions, we wanted to look into what kind of an oxidant would be able to degrade 6,2-FTS. We mainly took three oxidants, the first one being HP, which is hydrogen peroxide, PMS, which is peroxymonosulfate, PS, which is persulfate. And what we found was that you can see on the image on the top left is that persulfate performed amazingly well compared to peroxymonosulfate or hydrogen peroxide. We then did some parametric studies, which is the image on the top right. And what we found was that the higher the concentration of the oxidant, the faster was the degradation rate, and the amount of degradation was also higher. We then wanted to test the pH under which this compound would later degrade. So what we found was that unbuffered pH of 6.5 was working better than a pH of 10, where we know that base activation of persulfate can take place to generate certain amount of radicals. But even compared to that, having no activation or no buffered solutions, 6,2-FTS could be degraded. So we wanted to confirm this degradation by looking into several different factors. And the first one, which is one of the most confirming thing, is the fluoride release. So since the molecule contains a lot of fluorines in them, and so it's easier to analyze for that. So what we saw was we could nearly identify 23% of the fluoride from the molecule. So that confirmed the degradation. We also saw TOC removal. So there was nearly 8% TOC that suggested mineralization of the compound, essentially going to carbon dioxide and water. And the third and the final way that we could confirm this was by looking at the byproducts. And they produced, so when 6,2-FTS degraded, it produced a bunch of byproducts which ranged from a 7 carbon to a 4 carbon. But interestingly, what we found was that the total amount of byproducts that were formed were less than 1% of the original compound. So that created some amount of curiosity to identify what was really happening to these compounds, and were there certain intermediates or final terminal end products that we were not quantifying. So thanks to our collaborators from the organic chemistry department at the University of Texas at Arlington, they proposed a decomposition pathway for 6,2-FTS through conventional oxidation. What they proposed was that it undergoes several multiple transformations before it reaches the terminal end products. The terminal end products are what we essentially see from the labs. If we send a sample from an AFFF site, we basically get results for 6,2-FTS and just the terminal end products like PFOA or PFHPA or PFHXA or PFBA. And there are several unknown reaction intermediates that currently they are not being quantified because there are no analytical standards present for them. Also, as the carbon chain length increases of these molecules, the complexity also increases. This complex pathway that we have proposed is just for one compound degrading in the environment. Now imagine having a complex matrix with several different long chain PFAS compounds that would make it extremely hard to keep a track of what it's being transformed into. So some of these molecules that I have highlighted in red, which is circled, is basically certain reaction intermediates that we could identify. And the way we identified was by looking at the molecular weights. So I've written down the molecular weights of each of these compounds and how they would be seen on an instrument. The same instrument that's used for quantifying some of these compounds is what we could use to qualify the intermediates. And that's essentially what we did using an LC-MS-MS. So once we had gotten that degradation pathway, we then started looking into what the instrument was showing us and what molecular weights the instrument had come up with. And we could identify several different reaction intermediates. So we need to use this technique in a very conjunction manner where you need to have a proposed pathway before you can confirm that the instrument is actually able to see that. So that's what we found, and this was an amazing insight into what really happens to fluorotelomere compounds when they degrade in the environment under ambient conditions. So you have to kind of use them in conjunction to be able to confirm. So once we got this entire uh, degradation pathway, we then looked at its molecular weights. And then when I looked into the system, I could see a whole number of these molecular weights showing up on the instrument. So that confirmed that it was going through that degradation process. So that was really fascinating for us. And some of these perfluorinated compounds, they often require a higher energy source. And we could achieve that by applying advanced oxidation technologies. So in general, advanced oxidation technology consists of 3 steps. The first step is generation of radicals, and we could do that by simply activating an oxidant. an oxidant could be persulfate, it could be hydrogen peroxide. That's what the equations on the bottom are. So sulfate radicals can be generated by simply adding iron with persulfate to give you sulfate radicals. Or you could replace that with hydrogen peroxide and it would give you hydroxyl radicals. So once we generate these radicals, we would like them to interact with the PFAS because they are highly oxidizing in nature. And once they interact, they then degrade the PFAS by electron transfer. I started looking into the literature survey to see what kind of technologies were being used and how we could implement them under ambient conditions without having to use any of these energy sources. So what you see is that oxidants like persulfate or sulfite, they are often used with heat or electron beam or UV, supercritical conditions. So these external energy sources are a source of electrons, whereas the oxidants that are added are a source of radicals. So this technology of using electrons with radicals is some of the most promising ones. And in our first project, that's what we wanted to do. We wanted to incorporate electrons, and to do that, zero valent ion, which is used to a very wide extent for chlorinated solvents, is an amazing electron source. And for radicals, we could use persulfate. So we came up with this strategy. And what you see is basically zero valent ion incorporated into activated carbon. When it comes to PFAS, you need a fail-safe method where uh, even with reduced degradation, you're at least treating them or trapping them to a certain extent. So that's what we wanted to do. We wanted to incorporate the zero valent ion inside the activated carbon and generate radicals by injecting an oxidant. So the basic steps would first be adsorption of the PFAS, followed by generation of radicals because of activation of the oxidants and the zero valent ions providing electrons. And thirdly, we would have interaction of these electrons and radicals with the PFAS to potentially degrade them. So the first objective was to test the zero valent ion with persulfate or some of the other oxidants that we tested. And what we found was that the decomposition of uh, PFOA was to a higher extent. We were seeing removal of both PFOA and PFOS, but the decomposition of PFOA showed byproducts. So that was a confirming part for us, and we wanted to move further into looking into other compounds. And these were tested under mild conditions, so they were tested from 40 to 60 degrees Celsius. We then started looking into what was happening with the other compounds. So we did some adsorption isotherms, and what we saw was that we were getting high removal rates for 3 of the carboxylic acids that we tested and 3 of the sulfonic acids. So we tested a total of 6 compounds. And when you transform them into numbers, this is kind of what you see. So the trends that's commonly seen in the industry is that longer chain PFAS absorb a lot more than the shorter chains, and that's exactly what we saw. So the highlighted ones are PFOS. For example, we could nearly remove 60 milligrams of PFOS per gram of activated carbon, and we could only remove 30 milligrams of PFBS, per gram of activated carbon. The more interesting thing about this is also that they follow different isotherm models. So the type of adsorption that's occurring on the activated carbon is also different based on their carbon chain lengths. So that also makes a huge difference when it comes to adsorption or any kind of treatment. So we wanted to then synthesize this activated carbon. In order to do that, we use the incipient wetness method to incorporate zero valent ions into it. And what you see is that The circled part in the image on the bottom is a magnification of 7,000 times into the activated carbon to actually be able to see some of these zero valent ion particles. And the grayed out is basically the activated carbon. So this, we used different characterization techniques, but I believe the SEM images can give you a very clear image of the zero valent ion particles, because of which I put them. Also, we did surface area characterization like BET surface area and pore volume, and the reduction in the pore volume confirmed the synthesis of this reactive activated carbon. So you can say that. We then wanted to test this system into in the aqueous matrix and in the water and soil matrix. So fortunately, we saw similar results in both of these systems. We were seeing essentially decomposition of the carboxylic acids and no transformation of the sulfonic acids. The other interesting part was that in the aqueous matrix, we were able to see decomposition inside the pores of the activated carbon, and we confirmed that basically by extracting some of the PFAS from this activated carbon. And we were also seeing decomposition in the aqueous matrix, suggesting that there were reactions happening outside the activated carbon as well. So, this kind of confirmed our speculations that it's highly effective for carboxylic acids, whereas for sulfonic acid, it's a lot more challenging. Even achieving mass balances for short chain compounds can be challenging, because once they adsorb, they are not easily desorbed to be able to quantify them. Then the question was, now that we are seeing high degradation rates, but we required a certain amount of temperature for it. And the factor of temperature is a huge burden when it comes to cost, when it comes to applicability. So I wanted to look into how much is it really dependent on temperature. So one of the most common techniques or highly effective techniques is persulfate with heat for the degradation of PFOA. So now the question was, how can we completely remove the factor of heat? And that's what I wanted to see. So I started reducing the temperature each of my reactions, so I could tell after what point I could essentially not see any more degradation. So 100 degrees is pretty much the boiling point of water. So at 80 we could see, at 80 and 60 we could see essential complete removal or decomposition of PFOA after 24 hours. And as you reduce the temperature to 40 degrees Celsius, the decomposition was only 80%. And when you reduced it from 40 to 20, there was essentially no reaction happening, so there was no degradation. And I must also mention that persulfate can be activated by heat, so it's essentially generating sulfate radicals under these extreme conditions. So now the question was, if sulfate radicals are working to degrade PFOA under high temperatures, why cannot we do that under ambient conditions? And I started looking into several research papers and started going back uh, decades to be able to answer this question. And I found the right combination. So I'm essentially showing three activators over here, which is the Fe, which is like a modified Fenton reaction, cobalt, and silver. And what we saw was that silver was the most effective in decomposing PFOA under ambient conditions in combination with persulfate. So it's a simple bucket chemistry reaction, as you can call it, just by adding some silver homogeneous ions, so you can get silver sulfate in combination with persulfate, was able to degrade PFOA. And up till now, researchers have often introduced high energy intensive technologies to be able to achieve this. So this was really a breakthrough moment to be able to say that we could degrade PFOA under ambient conditions. So we then wanted to look into how many other PFAS can we degrade using this technology. And what we found was that it could work with PFNA, which is a 9-carbon carboxylic acid, that was degraded to essentially 80% over 48 hours, just by ambient conditions. We saw degradation of PFOA, like I showed previously, and we also saw degradation of PFHPA. PFOS did not essentially react in the system, and that's primarily because of the reaction mechanism, and it's selective towards carboxylic acids. But this was a huge breakthrough. We could confirm this by looking at some of the byproducts. So when PFOA degraded, we could essentially see different byproducts ranging from PFHPA, which, like I mentioned, is a 7-carbon, to PFBA, which is a 4-carbon. So we could also see fluoride in the system. And that was true for all of the 3 compounds that degraded. So that really confirmed this entire process of decomposition. So when we look at decomposition of these compounds, or use Fenton reactions, we often think of these metals as purely as an activator, and we miss out the fact that it could also be acting as a catalyst. So these metals can also be very good catalysts, and that's what was happening in this reaction. So what I'm trying to show in this image is that PFAS, all of the reactants that I was adding were basically colorless in the solution. So PFAS, persulfate, silver, they all dissolve very well in water, and you can't even essentially see them. But as soon as I added all 3 of these reactants, within 30 seconds or within a minute of the reaction, the solution changed to black. So that was telling us that the silver was undergoing certain amount of transformation. So that's the reactions that I have shown on the bottom. So the equations basically suggest that silver 1 was going to silver 2 by giving an electron to the persulfate to activate it. So that's what we see. Within 1 minute, you start forming these silver 2 oxides that play a role as a catalyst. And then within 48 hours, they essentially go back to silver 1. And that has huge implications when it comes to applying them in the field. If used in the appropriate manner, we would essentially could just keep on adding oxidants to be able to keep transforming the silver, activate the persulfate, start generating radicals, and degrade PFAS. So the question was, why was silver working so well? And why weren't some of the other catalysts that we were adding, or activators, why weren't they working so well? So what we found was that looking at the fate of persulfate, we could see a drastic change in the concentration of the oxidants. So what you could see out here is this is a simple iodometric titration to look at how much persulfate is left in the system. So the darker the color, the higher the concentration. So this is at time 0. The image on the left is at time 0. And after 48 hours of the reaction, what you see is that Fe and cobalt were only activating the oxidant to around 20%, but silver was essentially activating persulfate by 80%. So there was near complete consumption of persulfate over 48 hours. And that confirmed the generation of radicals to be able to attack PFAS. So that was a huge breakthrough. And I think this is something that could potentially be used for degradation in the environment. So moving on to currently what we are doing in our treatability lab, this is me conducting reactions. And we recently expanded our lab by another 2,000 square feet. It can handle many of our new projects, which are some of the treatability studies we do, and some of the new and upcoming R&D research and development programs that we're undertaking. So the first one that we are working on is the in situ chemical oxidation. For that, we have a provisional patent file. It's the combination of a unique metal oxidant that we can remediate PFAS in situ in affected sites. Secondly, we are looking into electrochemical oxidations. They are highly effective. They are non-selective in a manner, and they can degrade a wide range of PFAS. So that's the advantage of that. We are also looking at improved PFAS adsorption. So we have proven this to a particular class of PFAS, and we can improve the adsorption capacity of the GAC systems by nearly 5 times of what they originally can. And finally, we are looking into PFAS degrading regenerative techniques of for GAC. So I would like to explain that in some of the other slides. So for the first one, we have a provisional patent filed for it. It's currently in the phase 2 research and development. We plan on trying this out in the field later this year, and it's shown to degrade several different upcoming classes of PFAS as well, and it's highly effective. Secondly, the super sorbents for capture and destruction would be for GAC systems. So we would have a modified GAC which would contain catalyst in them, and once they are completely saturated with PFAS, we could essentially regenerate them using a simple oxidation technique. So it's one of our sustainable initiatives. It could certainly implement it on a large scale and regenerate the GAC systems in situ without having to be sent for regeneration at extremely high costs and energies. So it's a simple trap and treat method that we've come up with. We also have a provisional patent filed on the electrochemical oxidation system. It's highly effective in degrading. We are currently in the phase 2 development of this research. We've shown degradation of multiple classes, and we have a unique combination that would be able to do that. So prototype is anticipated this year, and we are really looking forward to that one. So in conclusion, what I would like to say is that fluorotelomers are significantly easier to degrade, but they produce several PFAS intermediates that may be harder to treat. Carboxylic PFAS can be degraded under ambient conditions, like I showed before, in using a silver and persulfate combination. And silver behaves as a catalyst, so that when we can potentially re-inject oxidants to be able to degrade PFAS. And the most amazing thing that came out of this research was that although we can degrade this whole new class of PFAS, which is the PFNA, the PFOA, all the carboxylic acids, and they are highly used in certain industries like the coating and the specialty polymers. So all of these insights that we got were highly effective, and I would be more than happy to answer any questions that anyone might have.
Thanks, Akshay. That was fantastic. Want to ask Jessica Bennett, can you check over the chat feature and look for questions there? And anyone else, if you have a question now, you are welcome to do the raise your hand thing in Microsoft Teams, and glad to have Akshay answer questions.
We don't have any questions in the chat yet, but please feel free to enter. Tom Blaney, I see you have your hand up. You can unmute yourself.
Yes, thanks. I don't know if I caught it or not, Akshay, but I was wondering, when you're doing the regen of the carbon, are there any byproducts that you have to get rid of that might be hazardous or not?
Yeah, that's a good question. So we are in the phase 1 of that research. So we are actually conducting those reactions as we speak. And once we get some insights into that, I would be more than happy to share it. But in my opinion, I think they would be degraded under because the interesting thing is that they all produce carboxylic acids. No matter what compound you kind of degrade, they all end up with carboxylic acids. So, and this treatment technology can certainly degrade all of those carboxylic acids, and that's what we've shown.
Great, thank you.
Mitch Gertz, you can unmute yourself. Go ahead.
Yeah, okay. Akshay, question, what levels of concentration of the PFAS have you been dealing with? We're dealing with PFNA levels upwards of 20 parts per billion.
Okay. Yeah, actually PFNA, what we tested was from 1 to 10 milligrams. And
Okay.
that was primarily because, to give us an understanding, because fluoride has a limitation of its detection limits. So to confirm some of our byproducts and the fluoride generation, we had to do higher concentrations, but it's highly effective in those concentrations.
Okay, good. Thank you.
We have a question from the chat. Who is from Beth Baddock? Who is funding the current research, and are there project sites that have been identified for field testing?
We are currently in talks with some of our clients, and we are pretty close to fixing a site, I would say. So I don't know if I could disclose, but I think we have something in mind that would work out later this year.
And I guess in terms of the question about the funding of the research, is that being funded by clients or internal or external sources?
Oh, all of this is, so the amazing part is that Parsons has an internal research and development program. So we are completely self-funded. So, we have the freedom of being able to implement or look into new techniques, new field testing pilots. So we could do a whole lot of stuff. So it's our own funding, yes.
Okay, great. We have another question from the chat from Stephen Grease. Any thoughts on why the longer chain carboxylate molecules were degraded better than the shorter molecules?
Right. So the interesting part is that as the chain length increases, the bond dissociation energy reduces. So because if you can imagine, the functional group is where the breaking happens. So when it's a longer molecule, the functional group is so much more, it's further away from some of these carbon fluorine bonds. So that is what makes it more susceptible to degradation. And as the chain reduces, the functional group is so much more intact. So some of the other fluorine molecules kind of stabilize the functional group, and that's what resists the degradation, essentially.
Okay, that's really informative, Akshay. If there's any more questions, let me see. So I actually had a question. So have you looked at any other metals aside from silver?
Yeah, so what I showed was essentially a very summarized form. I have tested hundreds of combinations before I actually got to it. There have been very few research studies comprehensively done to identify other potential combinations that could work. So I could pretty much count them on my fingers on how many research studies were done on proper metal oxidant combinations. So yeah, I tried a whole lot more.
Were there any that were, at all promising, or they just, you kind of wound up looking at silver as really the only one with good viability?
So the interesting thing is that silver acts as a catalyst, and it kind of latches on to the carboxylic acid. So that's the understanding that we could get, was that it's highly selective, but it's very efficient. So when we add certain kinds of metals, they don't necessarily act as a catalyst. So even though there is all these oxidants being generated, unless you can effectively transfer them to the PFAS, which is the catalyst role, if that's not happening, then the radicals are not so effective in degrading the PFAS.
Okay, thanks. If there are any more questions, please feel free to raise your hand or enter a question in the chat box.
And if there are no more questions, Akshay, could you advance one more slide?
Yes.
So I wanted to put in a plug for our next presentation, which would be on May 12th, same time, same place. Ed Heisey, Bruce Henry, and Brian Blicker are with our federal group, and they will be discussing sulfate-enhanced bioremediation of fuel contamination at a forward operating location in Galena, Alaska. I think you'll definitely want to be able to join us for that as well. So one last call for questions, and if not, appreciate everybody's time. Akshay, thank you very much for the presentation, and we will see everyone next month. Thanks, everybody.
Thank you.
Thank you.
Thank you.
Thank you.